Yes, thanks a lot for offering me the opportunity to talk in this seminar. So I will present a joint work with Marc, Levine, and Srinivas. So the general setting where this all takes place, or the kind of problem that we're interested in, this quadratic enumerative geometry, which it's a relatively new field, which sort of comes at the intersection of classical enumerative questions and motivic homotopy theory. It's also called sometimes refined enumerative geometry or A1 enumerative geometry. So so maybe one place to start is with the classical setup. And so one way to think about classical enumerative geometries, we attach numerical invariants to algebra geometric situation. And there are roughly two classes of invariants, of two ways to produce this kind of invariant. One is by topological methods, so some are intersection numbers, and then these intersection numbers are somehow refined into Chern classes, into algebraic cycles and invariants of a motivic nature, and on the other side you have invariants of a coherent nature, so attached to vector bundles or K-theory classes. But at the end of the day, we want numbers, and these numbers live into the group of integers. But this group of integers, it's realized on these two sides in either the group of zero cycles of the base field, or the group of K-theory classes of the base field. And so some of the most interesting aspects of enumerative geometry is the relationship between the two sides. And I will start with one such relation, which is in some sense the algebraic geometry version of the Gauss-Bonnet formula. So if you have a smooth projective variety of a field, you can start with the topological Euler characteristic of X, which you can realize with any cohomology theory. So either singular cohomology if you have the complex numbers, or L-adic cohomology otherwise. And then you know that this Euler characteristic can be written in many different ways. And for instance, you can go through the following equalities. You can use the Lefschetz trace formula for the identity to write this as the self-intersection of the diagonal inside X cross X. And then using some of the self-intersection formula, you can write this in terms of the Euler class of the tangent bundle, and it's the degree of the projection to the point of this Euler class. And then using the Deligne-Milnor formula, you can write this in terms of coherent cohomology, namely as an alternating sum of odd numbers. And one of the key result that we will use in this later in the talk will be a quadratic refinement of this result, which is due to Levine and Raskit. So yeah, so the question is, given this numerical invariance, can we refine them to a quadratic setting? And this means to lift them to the Grothendieck-Witt ring of the base field along the rank map. And this Grothendieck-Witt ring in this sort of geometric setting, it will appear in some sense either as an Hermitian K-theory group of the base field, or as the so-called oriented Chow groups of the zero cycle of the base field. So in this seminar, I think it's not necessary for me to spend too much time defining and introducing the Grothendieck-Witt ring. So, but as you well know, for any field which is quadratically closed, the Grothendieck-Witt ring is just the integers, and so this means that this quadratic enumerative geometry, or whatever it turns out to be, has to be an arithmetic theory. It's only interesting for fields which are not quadratically closed. But it doesn't mean that it couldn't have interesting applications to complex geometry, because, for instance, it's certainly function fields over the complex numbers that have interesting Grothendieck-Witt rings. But so one nice context to where to apply this quadratic enumerative geometry is over the real numbers. So over the real numbers, this Grothendieck-Witt ring is just given by two integers, which are congruent mod 2, so via the rank and the signature. And in this in this setting, what will happen is that the rank always recovers the enumerative geometry over the complex numbers, so of the complex point after complexification, and the signature recovers some real enumerative invariants, so which are attached to some real algebraic geometry of the situation. But so, I mean, I'm talking about these refinements, so I should tell you where they come from. And one way to produce refinements is on the coherent side is Grothendieck duality. And so Grothendieck duality provides, or Serre duality or Grothendieck duality provide non-degenerate symmetric bilinear forms. And let's look at one example, which is so how to refine this coherent Euler characteristic of a smooth projective variety. So if you start with a smooth projective variety of dimension n, then you can look at this Hodge. So this Hodge number, we replace it by the Hodge cohomology groups. We put them in certain in the appropriate degrees, and so we can think of this as a. I mean, it's just a graded vector space, but we just think of it as a perfect complex of k vector spaces with trivial differential, and we equip it with a symmetric bilinear form, which is non-degenerate, using Grothendieck duality, or Serre duality in this case. So we take the cup product from this group to this group. We land into this Hn omega n, and then we use the trace map. And the class of this the class of this perfect complex with this non-degenerate symmetric bilinear form in the Grothendieck-Witt group is a quadratic refinement of the classical coherent Euler characteristic. This maybe looked a bit complicated, but in fact it's quite simple. So if n is odd, then in fact this form is always hyperbolic. It's always, I mean, in this case the Euler characteristic is always even. So, and you can divide it by 2, and then the class you get is always a multiple of the hyperbolic form. And if n is even, then it's hyperbolic, except there's one possible contribution of the sorry, it should not be n. It should be n over 2, which makes sense now that n is even. So there's only one potential non-hyperbolic contribution, which is in the middle cohomology. So hn over 2 of omega n over 2. And just to illustrate this principle that over the real numbers, so if you over real numbers, then the rank recovers the Euler characteristic of the complex point, and the signature recovers the topological Euler characteristic of the real points. And this is a result due to Abelson. So okay, so that's one way to get refinements, to get nice quadratic forms out of geometry, is to use Grothendieck duality. The motivic side of the story really comes from motivic homotopy theory, and this is where how this idea of quadratic enumerative geometry came from looking at motivic homotopy theory. So let me give you a kind of crash course or quick introduction to motivic homotopy theory. So this is a common framework that has been developed by Morel-Voevodsky and subsequently by many people. It's a common framework for cohomology theories in algebraic geometry. So we always have a base scheme B, which I mean very often is a field, but it's useful to have the flexibility of a general base. And for any such base scheme, we have an associated stable motivic homotopy category, which denoted by SHOP. So this theory of motivic homotopy theory, but I mean, as the name suggests, it's modeled of the stable homotopy theory of topological spaces and the category SH of spectra. And so I'm not really going to give you the definition. I can just give you some cartoon definition, which is maybe only useful if you've seen it before. But this at least suggests what the ingredients are. So in the topological setting, if you've seen this construction of spectra, you start by using the category of pointed topological spaces. On the category of pointed topological spaces, you have the wedge product of spaces, and in particular you have suspension, which is wedged by the product with the circle. And to get the category of spectra, you somehow inverse. You make this suspension, so wedge with the circle invertible, and this is what creates some of these spectra. And in the motivic, for the motivic analog, you start with the category of smooth schemes over the base. You look at pre-sheaves of pointed spaces over that category of smooth base scheme. Then you somehow you have to impose some conditions. So you impose a condition of Nisnevich descent for the Nisnevich topology and the conditions of A1 homotopy invariance. And then this now is the unstable motivic, pointed motivic homotopy category. And as in the topological setting, you invert something for the, sorry, I said wedge before, I meant smash, sorry, for the smash product, which is instead of inverting the circle, you invert the P1. So the resulting object is it's a tensor triangulated category. So tensor here is given by this smash product. And I mean, maybe in a bit more fancy terminology, but which is kind of useful because as a bare triangulated category, it's not always sufficient. So you have an underlying enhancement as a symmetric monoidal stable infinity category. So this category is kind of a mixture. I mean, by design, it's really a mix. It's a mixture of algebraic geometry and algebraic topology. So in particular, there are two natural sources of object in this category. You can take a base key, a smooth scheme over the base and a point with a point. So just a section, a B point. Then you have a functor called the infinite suspension functor, which is basically, I mean, you should think of it as the Yoneda embedding to get a pre-sheaf of pointed spaces, and then somehow taking the so-called infinite suspension spectrum of this pre-sheaf. So that gives you objects in SH of B. So this is the way that somehow the algebraic geometry over B is sent in this category. But on the other hand, you can take any spectrum in SH, and you can take some of the pre-sheaf, sometimes the constant pre-sheaf of spectra, and that also gives you objects there. So you get this mixture. So let's look at some examples of things that you can construct in this way. So as in topology, you have the basic building blocks of the theory are spheres. But unlike in topology, you have bigraded spheres. So because you have, as I said, you have these two origins. You can take the topological sphere and send it into your into SH. But you can also take some of the algebraic geometry version of the circle with this GM pointed at one, for instance, at a rational point, and then you can take a smash product of that. And this Q, so this GM will actually be the version in that context of the Tate twist. And now using this SPQ, you can define, for instance, homotopy groups in the same way that you would do in topology. So you can define bigraded stable motivic homotopy groups, and as in algebraic topology, the computing these groups is both very difficult and one of the basic problems that you want to solve in this context. Another important kind of spaces you can construct are Thom spaces of vector bundles. So if you have a vector bundle over your base B, then you can because you're in this world where you're in this world of pre-sheaves, you can do you can take colimits which are not really possible in algebraic geometry in the world of schemes. So for instance, you can take your vector bundle and you can contract the whole complement of the zero section. So you can take in in some sense the cofiber of the map from this thing to this thing, and that will give you an object in SH of B, and this object turns out to be always invertible with respect to the tensor, to the smash product. And one of them is already familiar to us. If you take a trivial vector bundle, then what you get is always this 2n sphere. But for a general V, it's not necessarily one of these spheres that we saw before. And the main, I mean, the role of these Thom spaces appears via this the Morel-Voevodsky purity theorem, which is one of the first non-trivial statement in the, I mean, in the story, which doesn't somehow follow directly from the ingredients that you put in the definition, but then you have to work quite a bit. So this tells you the following: that so if you have two smooth B schemes, and one is and a close embedding from one into the other, then you can do something very similar to what we did for the Thom space, but instead now we're using X and the complement of Z in X. So if X was a vector bundle and Z was its zero section, this would be a Thom space. And what Morel-Voevodsky tell you is that this is in fact always a Thom space, namely the Thom space of the normal bundle. And here, so this object, in the way that we've defined things, this lived now in SH of Z, and on the other hand, this left hand side lives in SH of B. So I have to do something. So I have to apply a functor which sends one to the other, and this is somehow the first hint of the functorality of this construction SH. So SH of for varying base schemes has a somewhat very rich functorality, which is this so-called 6-operation formalism, and this will turn up a bit later. But this one I won't really have time to go into it. And so one last important feature of SH is that, as in the topological setting, it's used to represent cohomology theories. So in the same way that, one of the main role of spectra in classical stable homotopy theory is to represent these so-called extraordinary cohomology theories. This is the same here. So for any motivic, for any spectrum, for any object in SH of B, you get an associated bigraded cohomology theory. So again on smooth schemes over B. So and this is obtained by the same formula as in topology. So you have to put your, and this is where also those spheres come in. And there are many familiar cohomology theories in algebraic geometry, which are familiar and less familiar theories, which are represented in this way. And so I'll just mention a few, just four, which are among the most important ones. So there is, for instance, a motivic spectrum HC, which is the algebraic geometry version of the Eilenberg-MacLane spectrum. And here I'll just make, for simplicity, I'll just assume that B is the spectrum of a field and a perfect field. And then the resulting cohomology theory is what is called motivic cohomology, and it's of Voevodsky or Suslin-Voevodsky, and it's isomorphic to higher Chow groups. So in this way, you recover higher Chow groups as morphism groups in SH. There's also a spectrum KGL, so which is the analog of the spectrum KU in algebraic topology, and which represents algebraic K theory, and in fact homotopy invariant algebraic K theory of variables. So on regular schemes, it's just Quillen's algebraic K theory, and as on singular schemes, it has to be modified appropriately because algebraic K theory is not homotopy A1 invariant, so it has no chance to be represented in SH in itself. You have to do something. And then you have variants of this. So in some sense, quadratic variants of these two theories. So you have a spectrum HC tilde, which represents what is called Milnor-Witt motivic cohomology, or higher Chow-Witt groups. And you have a spectrum, so which we could denote by KO, which represents homotopy invariant Hermitian K theory. So these two spectrums, so there are quadratic versions of the previous one. It's really a new phenomenon which has no counterpart in algebraic topology. So this is this is where all these quadratic phenomena in motivic homotopy theory somehow come from. So another important feature of this theory is the theory of orientations and characteristic classes. So I'll just say a little bit about this. So as I mentioned before, so if you have a vector bundle, the Thom space as an object in SH of B, it really depends on V. So there is this case for a trivial vector bundle where it's a sphere, but otherwise it's something different. But in some cohomology theories, I mean the cohomology theories that we have seen before, the situation simplifies quite a bit. So for instance, if you take the motivic cohomology spectrum, then and you take any Thom space and you smash it with the motivic cohomology spectrum, then you always get a sphere again smashed with the. So this maybe if you haven't seen these things written like this, is maybe a bit confusing, but this is saying that from the perspective of motivic cohomology, so of the spectrum HC, all Thom spaces are trivial. They are all the same as the Thom space of the trivial bundle, and the same holds for KGL, for homotopy invariant algebraic case theory. And we say that this, I mean, this is a kind of, yeah, we say that these two theories, motivic homology and algebraic case theory, are oriented or GL oriented. And for HG tilde and chaos, something very similar happens, except that you still have the Thom space of the determinant bundle, which survives this process, and which is not trivial. And we say that because it only depends on the determinant, we say that this HG tilde and KO are SL oriented. So it's kind of an abstract phenomenon maybe, but this has concrete consequences. So for instance, if E is oriented, there is a theory of Chern classes, which is you can develop in the same way that you develop theory of Chern classes for Chow groups and higher Chow groups. And so it's just it has exactly the same formal shape as the theory of Chern classes for Chow groups. And if you have an SL-oriented theory, then the situation is a bit more complicated. But what happens is that you can define twisted cohomology groups where you twist the cohomology by a line bundle. So line bundle because we had this determinant bundle before, and this is the definition. So how you can define twisted groups, and then you don't have Chern classes, but you only have. For my purpose, you only have one interesting characteristic class, which is the so-called Euler class. So it's the analog of the top Chern class, and it lives in one of these twisted cohomology groups, so twisted by the inverse of the determinant. So this theory SH of B, in general, it's a very complicated category. It sort of combines the notorious simplicity of stable homotopy theory and motivic invariance. So what can you do? I mean, there's really a lot in there. But so there are still ways to extract reasonable invariance, and one of them is this fundamental theorem of Morel, which tells you about somehow the pi zero of the zero sphere, or the stable pi zero of the sphere. So it tells you that the endomorphism of the sphere S00, which is the unit for the smash product, is the Grothendieck-Witt ring of the for when the base is a perfect field. And the map is actually very simple, but maybe for lack of time, so the map in this direction is very explicit, but the fact that it's an isomorphism is really is quite a deep result. So this fact can also be interpreted in the following way. So you have the unit map. I mean, these two spectra are, and in fact the four spectra, the four that I mentioned representing cohomology theories, they are all ring spectra. So in particular, they have a product, but they have a unit. So the unit maps are maps from the unit to HG tilde and to KO, and so these will induce maps on endomorphisms, and the endomorphism of HG tilde, they are just this Chow 0 tilde of the base field. So this is just a Grothendieck-Witt ring, and same for this homotopy invariant Hermitian case theory. And so one way to think about Morel's theorem is that it tells you that these unit maps are isomorphisms. So all this quadratic information can be detected both via these Chao-Witt groups and via this via Hermitian K-theory. And you should contrast this with the unit maps for HE and KGL, which what they induce is the rank map from K, because yeah. So you lose all the by passing to motivic homology or algebraic K-theory, you lose all the quadratic information. So this is why somehow these two theories, so these Chao-Witt groups and this Hermitian K-theory, they somehow play a central role in this quadratic enumerative geometry setting, because you have to use them, otherwise you lose all the interesting information. So, and another reason why this endomorphism of the sphere is interesting is that it's a receptacle for traces in SH. So let me just recall the general formalism of traces. So if you have a symmetric monoidal category, which so this all these SH of B's and so on are in particular, you say that an object is strongly dualizable if there is a strong dual. So it's an object, and together with evaluation and co-evaluation map, which satisfies some triangle identities, which I won't write down. So presumably you have seen this definition, at least in some context. But so when you have a strong dual, what you can do is form traces. And well, in fact, so if you have any endomorphism of a strongly dualizable object, you can do it. You start with the unit of your symmetric monoidal category, use the co-evaluation, use f on the x factor, and then use the evaluation. And this composite is, so it's an endomorphism of the unit object, and it's what's called a trace of it. So now if you apply this in SH, well, to apply this, you need some strongly dualizable objects. So let me just tell you what happens in SH. So the first result is that if you have a smooth projective morphism over the base, then the resulting object in SH, this resulting suspension spectrum, is strongly dualizable. And the dual is in fact given by one of these inverse Thom space. So this is why it's kind of important that the Thom spaces are invertible for the smash product. And as a consequence of this, you can when you're over a field, you can do much better. But so some of the proof of two uses one. But so over a perfect field, if of some characteristic, then any object which is constructible in SH, so which means that any object that you can construct, which is in the smallest triangulated subcategory, stable by direct factors, which contains the motifs or the homotopy types of smooth varieties, is strongly dualizable. And okay, there is this little caveat that you have to invert P if you're not in characteristic P, but I won't stress that point. And as a consequence of this, then you can define, you have a rich source of strongly dualizable object, and you can define the Euler characteristic, which is some of the main object of the talk. So if in fact using this result over perfect field, you can just think a little bit, you can define things for any field of characteristic different from 2. So you take a constructible object in SH of K, then you define this quadratic Euler characteristic as the trace of the identity map of this object. So, and if your field is not perfect, what you do is you pass to the perfect closure, and this induces an isomorphism on the Grothendieck-Witt ring. And so, yeah, you just define it by first passing to the perfect closure and then coming back. So that's one thing that works for anything, but you can do something which is more tightly connected with geometry, using this formalism of 6 operation that I mentioned. So roughly speaking, you want, I mean, as in topology, you want at least two different types of Euler characteristic, one which is the normal one, and one which is the compactly supported one. And using this formalism of 6 operations for SH, you can do this for any finite type separated scheme over K. So you can define these two, the usual Euler characteristic and the compactly supported one as this quadratic Euler characteristic of a certain object that you build from X using the 6 operation formalism. And the advantage of this compactly supported version is that, as in topology, it satisfies a cut and paste formula. So if you have this one of these finitely separated K scheme and a closed subscheme, then the Euler characteristic of this compactly supported quadratic Euler characteristic of X is the sum of the one for the closed subscheme and its complement. So now in this setting, I can state a very nice theorem, which is it's the quadratic version of this Gauss-Bonnet formula that I started with. So it's the following: so you have a perfect field of characteristic different from 2 and a smooth projective variety of sorry, this should be a P. A smooth projective variety of a K. Then this gives you a formula for this the quadratic Euler characteristic of X, as it's nothing else than this Hodge class in the Grothendieck-Witt ring that I mentioned before. So maybe let me just remind you what this was. This is this quadratic announcement of. Oh, I guess I already gave it a name, so I could just reuse this name actually. Sorry. So it's this Grothendieck-Witt coherent. Yeah. So this theorem really provides a quadratic refinement of this Gauss-Bonnet formula, these two ways of writing the Euler characteristic of a smooth projective variety. And the proof of this works in a very similar way to the proof of that I sketched before, except that you have to use an Euler class in Hermitian K theory. And this is what they do. They first relate this Euler characteristic with the Euler class in Hermitian K theory, and then they compute this push forward in Hermitian K theory, and they identify it with this Hodge. So now let's look at a concrete example of this computation. So I mean, okay, this gives you a formula, but you still need to identify what this is in concrete cases, and this is not so easy. But so there is one class of examples where it can be done, and it gives a nice formula. So it's the case of smooth projective hypersurfaces. So you start with some homogeneous polynomial of degree E, which is prime to the characteristic. So this, and you assume that it defines a smooth hypersurface in Pn+1. So in this case, you can associate to this the Jacobian ring, which is this ring is the quotient of the polynomial ring by the ideal generated by the partial differential of your defining equation. So this is still a graded ring, and in fact it turns out to be so it's a finite dimensional graded Gorenstein algebra. So this means in particular that the top non-zero graded piece is one dimensional. So this is and in fact so it turns out to be in this degree. And moreover, in this situation, there's a canonical generator of this space, which is called the Scherrer-Storch form. And in fact, so the general definition would take a few extra lines, but in characteristic 0 or in large enough characteristic, in fact, you can define it quite easily. You can take the Astron matrix, which gives you in fact, suitably interpreted, gives you an element here, and you just have to divide by the dimension of this, but this only makes sense when it makes sense, so when it's invertible. And using this this canonical generator, I mean, the fact that it's Grothendieck tells you that there you get canonical non-degenerate symmetric bilinear form, which is defined so this like this, which is defined simply by the form applied to a pair x xy is, I mean, what you do is you form the product in the ring, and if it is in the top degree, and if it's a multiple of the if it's in the top degree, then it's a multiple of this canonical generator, so by some lambda, and then the form just spits out lambda, and otherwise it's 0. If it's not, if it's in the wrong degree, it's 0. So now a theorem due to Carlson, Griffiths, and also Dolgachev, and there's a little bit. There's a little extra bit in our paper. Is the computation of the Hodge of this quadratic form on the Hodge cohomology of the hypersurface in terms of this Jacobian form, and it takes the following form. So if n is even, then it's essentially it's telling you that this thing is essentially this Jacobian form up to this the multiple and an additional sum, and when n is even. And then there is an analogous statement which I won't state because it's more technical, and it's really parallel for hypersurfaces in a weighted projective space. And the idea of the proof, this relies on Griffiths' identification of the primitive cohomology, or the primitive Hodge cohomology of X in terms of residues of differential form on the complement. So this is a classical result of Griffiths, which was then somewhat upgraded by Carlson and Griffiths to a result about the cup product, at least in characteristic 0, and then it turns out to work whenever the characteristic is prime to the degree of the hypersurface. And okay, I won't insist on this. Okay, so now we can come to this Deligne-Milnor formula question that we address. So this Gauss-Bonnet formula for the quadratic Euler characteristic, so it gives a nice formula for the smooth projective case, but it seems quite difficult in I suppose as in classical enumerative geometry or classical topology, it's quite difficult to give general formulas for the Euler characteristic of a singular space. And so one situation that you can look at is just a smooth variety degenerating into a isolated singularity. So this is the context of this Deligne-Milnor formula. So here's the setup. So you have over a discrete valuation ring with generic point eta and close point sigma, and you fix a uniformizer. This will come up later. And so you have your family, which is a flat separated finite type morphism of some relative dimension n, and so you want the situation to be somehow as minimally singular. So the minimal amount of singularity you can have in this situation is that the total space is regular, the generic fiber is smooth, and then the special fiber is smooth outside of one point, and which is also a rational point. And okay, so here this one point and the fact that it's a rational point, these are just for simplicity. I mean, you can write statements which take care, which work for isolated for finitely many isolated singularity which are not necessarily rational. So in this situation, you have what's called the Milnor number of the singularity, which, so in general, it has a definition which is maybe not so enlightening, but at least maybe the thing to notice is that it's a purely coherent definition. It's just in terms of coherent cohomology or coherent sheaves on X. So it should be a OX. So there's a more enlightening definition which you can see if you fix a system of local parameters your regular total space around the singular point. Then you can define a Jacobian ring, which is very analogous to the previous one, except that now it's a local Jacobian ring. So you take the local ring of X at the singularity, and now so you want to you want to function. So you use your uniformizer to turn this to turn your morphism there into a function. And then you can take, because you have this system of local parameter, you can make sense of the partial derivatives, and that's your local Jacobian ring. And then this Milnor number is just the dimension of this Jacobian ring over. So this is naturally an algebra over the residue field, and yeah. Okay, so now the result in this situation, so which is a classical result of Milnor over C and of Deligne in more generally. So for this, you have to suppose that S is of equal characteristic. Then this relates this coherent quantity, so this Milnor number with a topological one. So there are two versions of this. There is a kind of a local version and a global version. Maybe let's start with the global version, which is a bit simpler to understand. So for this, we assume that F is also proper. Then this Milnor number is just measure the difference between the Euler characteristic of the generic fiber and the special fiber. So up to a sign, and there is an additional term, so-called Swan conductor, which is 0 in characteristic 0, and otherwise it somehow measures the possible Wald ramification phenomena. But it's not really important for our purpose. So, I mean, it has to be there in positive characteristic, but for us it's not going to really matter, and it's kind of mysterious what it should be in our context. So that was the global version, and then there is a local statement which is formulated in terms of the so-called vanishing cycle functor. So, for instance, the Lehalleur vanishing cycle functor. So this in this context is actually so in general, this vanishing cycle functor is a complicated object. It's a complex of Lehalleur sheaves on the special fiber. But in this situation of isolated singularity, it's actually a skyscraper sheaf. And what we're just looking is skyscraper sheaf maybe shifted. So we're just looking at the dimension of this finite dimension.
Perhaps a silly question, but this -1 to the power n, n is the dimension, or?
Yeah, the relative dimension.
And so, but the left-hand side, this mu is always positive, or
yes,
not? I mean,
yes, yeah. So this is this is why I said this is a shift of like it's a skyscraper shift, but put in degree, I guess n. So that's why.
Okay, so there are some shifts. Okay.
Yeah, there is a shift.
All right. Thanks.
And in this case, you see that this can certainly be positive or negative. And in fact, the formula tells you whether it's positive or negative depending on n. So this is Deligne formulation of the situation, and in Milnor's formulation, this was the over the complex numbers. This was the Euler characteristic of the so-called Milnor fiber of at X0, which is a topological object you can associate to an isolated singularity, and which is somehow this vanishing cycle formalism somehow translates in algebraic geometry. So this is actually expected to hold always. So these two formulae, including in mixed characteristic, but this is still open in general. And so there are this local and global formula, but in fact the local one implies the global one essentially by push forward to the base. So a basic property of these vanishing cycles is that they commute with proper push forward, and that basically that implies this. Okay, so now we would like to understand the possible quadratic refinements of this situation. And so I will first focus on the global formula for f proper and only in the equal characteristic case. So the first obstruction to a possible refinement is that, I mean, we look at this formula, we have these two terms, but now they live in different rings. They are not integers anymore. So one lives in the Grothendieck-Witt ring of the generic, the residue field at the generic point, and one at the closed point. But what we have is a specialization map on Grothendieck-Witt ring. So, and this really depends on the choice of this uniformizer. So this specialization map is the unique ring homomorphism with the following two properties. So first of all, if I take a unit, something which is actually a unit in the S, then I can just reduce it, and that's what the specialization map does. It takes the class of this one-dimensional symmetric bilinear form, and it just sends it to the same thing with the reduction. But it has to be normalized for the non-units, and the normalization is given by this t. So it has to send the class of t to 1. So now what we can do is we can specialize the generic term, and we get something now which lives in the Grothendieck-Witt group of the closed point. So now on the other side, what we can do is in this equal characteristic setup, at least we can use the theory of localized Euler class. So the theory of Euler classes for instance, in the Hermitian case theory, there is also, I mean, in the same way that there is a theory of localization of Chern classes. You know, if you have a section of a bundle, then you can somehow localize for instance, the top Chern class to the zero locus, or the vanishing locus of this section. There is something similar here, and basically what you do is this has been done by Wickelgren and also by Bachmann, and in a later refinement of this by Bachmann and Wickelgren. So you can define a quadratic version of the Milnor number. So as one of these refined Euler class, it's roughly speaking, it's something like this. So you take the Euler class of the omega 1 of x over k. So now, because you're in the equal characteristic situation, you can, okay, yeah, basically you can think of the total space as something over k. And then in this you have a section in this context which is just df. So that will localize thing precisely to the critical, the zero locus of df, which is the critical locus of f, which is just the isolated singularity in our case. And then this in fact, to get something in this Grothendieck-Witt of k of x0, you have to somehow trivialize a line bundle, and for this you use the uniformizer. So this really depends on the uniformizer. So you get something in the Grothendieck-Witt of the residue field of x0, but because we have assumed that x0 is a rational point, but again this could be we could get around this, but this is then just a class in Grothendieck-Witt ring of k of sigma. So now we have two invariants, which both live in the same ring. But this is kind of an abstract thing, but in fact it turns out to have quite a concrete description as a Scherastor form of a very simple. So it's very similar nature to the previous discussion on this Jacobian ring of an hypersurface. Now you have this local Jacobian ring. And again, you can construct a symmetric bilinear form on it by the same construction. Okay, so now there are at least two natural questions in this setting. So maybe the first one is there a quadratic refinement of this one conductor term, which I have not mentioned. And in this, so even if we can't answer this first question, so in the situation where the Swan conductor is 0, does this Deligne-Milnor formula live to the Grothendieck-Witt ring, given that we have quadratic enhancements of both sides? So the answers at this point are, the first one is I have really no idea. So this is really really a complete mystery to me, how you could get these Swan conductors to live to quadratic forms. But even in terms situation where the Swan conductor is 0, the answer is no, and so the naive lift of the formula does not hold. So what does hold? Well, so here is what we can prove. So this is the case of somehow a very simple type of singularity, essentially a cone, where the singularity is a cone over a smooth hypersurface of some degree. So this is the situation where you have an hypersurface defined by this equation, and you assume that the hypersurface. So this is now an hypersurface in a one-dimensional lower projective space is smooth, and so really the geometry is like this. Well, maybe this is the quadratic case, so the case E equal 2, but still in general it's very similar. Then so now we can compare the two sides. So we had this term and we had this term, and they are equal, but there are this correction term. So there is, first of all, there is kind of a multiplicative correction term. So you can also write this. I mean, you can, here I've separated them, but you can also, and this is maybe probably a better way to do it, you can group them together. But there's also an additive correction term of rank 0. I mean, just to be rank 0 because the classical formula also. Okay, so that's then there is an analogous statement for hypersurfaces in a weighted projective space. So, but it's quite a bit more complicated to state, but it's a very similar statement. So what this means roughly is that you replace this f by something which is not homogeneous in f, but which is weighted homogeneous. So you give weights to x0, x0 to xn, which are not all 1, but some integers, and this has to be weighted homogeneous. And then finally, there is maybe a more satisfactory version of this result. I mean, this result was somehow for a very specific type of equation, but what happens is that the formula still holds if you have a situation which is locally of this type. And here locally, for instance, means that in the case of 1, what you can do is you can assume that you have finitely many isolated singularity, and what you assume geometrically is that there are, if you blow up one of the singularity, then it becomes it's essentially resolved by one blow up. So if you blow up, you have the strict transform and the exceptional divisor, and they are both smooth and they intersect transversely. So it's a very special type of singularity. In some sense, it's one of the simplest one you can have, but that's the case where we can compute everything. And this last statement, so this is mostly due to Ran Azuri. So building on the previous cases, but yeah. Let me just say a word about the proof. So the proof just is a direct computation of both sides. So it's maybe not so satisfactory, but that's how we can at least find this discrepancy between the two sides. So the basic point is that in this situation, as we say, we have a very nice resolution of singularities, and so we can do cut and paste arguments both on the. So we use this compactly supported thing to do cut and paste, and we can do cut and paste both on the singularity and on its resolution, and then that gives you formulas. Then that reduces the computation to the two computations of Euler of this quadratic Euler characteristic for smooth hypersurfaces, and then so we use this this result about in terms of which gives you formulas in terms of Jacobian rings, and then you have so on this let me maybe say so now at this point on this side you have something which is expressed in terms of this global Jacobian ring of smooth projective hypersurfaces, and here you have something which is expressed in terms of this local Jacobian ring. But in fact, this local and global Jacobian ring for this cone singularities, they are very closely related, and then you just compare the two and you get the statement. So that's the argument that's used for this first two parts, and then for the last part, so there are two steps. So the first one which we did was to relate. To localize the situation a little bit, which is so we prove a general statement. I mean, this holds essentially without this holds in equal characteristic 0, but without any assumptions on the singularity besides the fact that they are isolated. And so this is a relation between this term, this difference of Euler characteristic, and the Euler characteristic of the so-called motivic vanishing cycle, but this time in SH. So Ayub has constructed an SH version of the theory of a vanishing cycle, and so this lives now in SH of the. And again, it's because we have an isolated singularity. I mean, this should be thought of somehow as the fiber of a more global object, but which in the case of isolated singularity is just concentrated on the singularity. So that's one thing. And then what Azuri did was to globalize this as I mentioned before, using, first of all, he used the relationship between Ayub's vanishing cycle and the theory of motivic integration of Denef and Lehalleur. So this is based on result of Ayub, Ibora, Sebag. So they prove a general relation between the motivic vanishing cycle and some of the Euler characteristic of the motivic vanishing cycle and motivic integration, and then there is a computation in motivic integration. And my time is almost up, so let me just conclude by saying that so this is just a toy model in some sense, but already in this case of very simple singularity, we have these mysterious correction terms, and we have no guess at this point for the general case. And maybe one thing that I should say is that this enumerative, this quadratic enumerative geometry is there are many other things that have been done. So, and this is only one small corner of this field, but yeah, there are lots of other interesting results and interesting questions that are open. So I'll stop here. Thank you.
Thank you very much. Thank you very much. Let's thank a speaker. So is there any question? Any question?
Simon, can you go up just to the previous slide?
Yeah.
With the vanishing cycles of Ayub.
Yeah.
How do those depend on X?
On X.
I guess just the notation on the right hand side. I see this phi t of S naught, and I'm trying to understand.
Yeah, sorry. So yeah, so this should be sort of so this is a functor from sh of x to sh of the special fiber.
Okay.
And so it's applied to just the unit on X.
Great.
Thank you. I should stress that here it's important that the construction of Ayub does depend on T, and indeed it's you really see it because it gives different forms, different Euler characteristics.
So more questions? questions?
There were some questions in the chat.
Oh, yeah, right.
Yeah, sorry, I'm just having a look. Yeah, sorry, yeah, Kyle is right. Yeah, and is not functorial. So yeah, but still there, yeah, you have to see to apply pi 0 instead. Okay, I think that was it. Oh, I can't scroll back the chat. Okay.